Well, welcome back to Math 118, everyone. Here, the first part of Lecture 13, we're going to take a look at exponential and logarithmic equations. Okay. And we're going to sort of use these tools, these properties of logarithms and exponentials, to solve various equations regarding them. And then in the second part of this lecture, we're going to sort of take that and apply it to some real-world models that we use, out in the wild when we're trying to understand various natural processes. And one of the core things that allows us to do all of this manipulation is that the exponential and logarithmic functions are one-to-one, right? Because what that allows us to do, okay, is say we have a to the x equals a to the y, okay? Well, what we can do is we can directly say from this, okay, this goes both ways, that this means x equals y, right? And it's worth thinking just a little bit why, right? Okay, yes, we do know it's one-to-one, so that should be true if we treat, a to the something as a function, right? But let's see if we can figure it out, right? Well, if we're trying to drop these exponents, right, the natural thing to do would be to take the logarithm, right? So let's take log base a of a to the x, and I do it to both sides, right? That should be y, okay? But what this means, right, one of our rules of exponents is I can take these guys and I can drop them down. So that gives us that x times log base a of a, and that equals y times log base a of a. But if you remember, when we're taking log base a of a, that just equals 1, right? So those ones cancel, and you have that. Okay. Now again, it's worth noting that these all actually go both directions, right? One of the nice things about equals is that it goes both directions, right? But so there you have it, right? If you take this little detour through logland, we can show algebraically what we kind of already knew to be true up here, okay? So without further ado, let's use this to solve some problems. Okay, we're going to start with a bunch of exponentials, and then we'll move to logarithms in a little bit. Okay, so we're wanting to find all real solutions to the following equations. Okay, so our first one, let's say something more simple like 5 to the x equals 125. Okay, so what we're wanting to do, right, sort of using this idea here, we're going to see if we can write 125 as 5 to the something. Okay, well, we have 5 to the 1 equals 5, hoping that it's going to be a whole number. 5 to the 1 is 5. That's, 120 off. We have 5 to the 2 is 25. Getting there, still off by 100. But if I have 5 25s, that's indeed 125, right? So that means we can write this as 5 to the x equals 5 cubed, or x equals 3, just like that, okay? For this next one, let's keep our bases of 5s, but let's go a little bit more complicated. Say 5 to the 2x equals 5 to the x plus 1. Now, if you're trying to, solve this using, a bunch of different algebraic means, maybe guess and check, a bunch of different ideas, that's going to get a little complicated. But if you notice, we have this handy expression right here, okay? So that just means that 2x equals x plus 1. And now this is a much simpler algebra question that gives us the answer of x equals 1. And I will box both of our solutions. Okay. Let's take a look at our next one. Okay. It's telling us to find an exact solution for the following. Okay. Here's our first one. We'll say 3 to the x plus 2 equals 7. Well, our previous trick doesn't quite work so much anymore, does it? Right? Because we have 3 to the something and 7 to the something. So that doesn't quite work, but if you remember, one of the really nice things about logarithms is that they can strip these exponents, right? So let's take the logarithm of both sides. Right, we'll just do the common log. So we have the log of 3x plus 2 equals the log of 7, right? That's totally valid, okay? I can take this exponent and I can shift it down. So we get x plus 2 times the log of 3 equals the log of 7, okay? Now, I don't, off the top of my head, know the value of log of 3. But what I do know is that it needs to be strictly greater than 0. And because it's strictly greater than 0, I can divide by it, right? So that means that when I divide by it, I get x plus 2 is log 7 over log 3, okay? And now I can subtract 2 from both sides and get x log 7 over log 3 minus 2, okay? And when this question asks us to find an exact solution, right, what it means is it's looking for something like this, right? It's not asking you to put it in your calculator or round to so many decimal places. We're looking for, the exact value of it. And actually going forward, unless I ask for, a rounded value, always just provide the exact solution. Okay? Simply because this exact solution, well, A, it's more exact, but it kind of, in a sense, holds a little bit more like truth as to what the answer is versus what the answer approximately is, okay? Let's go to part B on this question, and let's find our exact solution for 8 times e to the 2x equals 20, okay? So what I want to do, seeking to go through a thing like this, right, is I want to try and isolate this e to the 2x. And I can do that, right, by simply dividing by 8. So we get e to the 2x equals 20 over 8, or if you prefer, 5 over 2, okay? And now what I'm going to do is I'm going to take the natural log of both sides, right? Having this base of e here sort of is asking us to take the natural log, right? Because when we do the natural log of e to the 2x, it's going to be the natural log of 5 halves, right? I can drop down this 2x, comes the natural log of e, it's the natural log of 5 halves. But remember, the natural log of e is just 1, right? So that means that this 2x is isolated, and we have that x is the natural log of 5 over 2 all over 2, and that is our exact form. Okay. Let's try one similar to this that is a little bit more involved. Okay. Let's try instead, say e to the 3 minus 2x equals 4. Okay. But this actually proceeds sort of the same way. Having this e, well, that kind of clues us in. Why don't we take the natural log, right? So we have the natural log of e times 3 minus 2x is the natural log of 4. Dropping down our exponent, 3 minus 2x, the natural log of e. We already know it's just going to be 1. And that equals the natural log of 4, Rearranging this, doing some algebra, we get that x is 1/2 times 3 minus the natural log of 4. You know, we move this 3 over here, divide by a -2, and there we go, okay? But let's introduce something a little bit stranger, okay? Let's say we're doing d here. What about e to the 2x minus e to the x minus 6 equals 0? Okay, this is a bit stranger, okay? But here's what I want you to notice. E to the 2x is e to the x squared minus e to the x minus 6 equals 0. This is a quadratic, but the thing that we called x previously, we now just have e to the x, right? This is a quadratic in e to the x. So what that means is I can do a little u substitution, and you can factor this into u, which is e to the x, minus 3, plus u, which is e to the x, plus 2 equals 0, right? And this is going to break into two cases, right? If their product equals 0, well, then that means that one of two things is possible. E to the x minus 3 equals 0, or e to the x plus 2 equals 0, right? And so this means that e to the x equals 3, or x equals the natural log of 3. Okay, that's one answer. You'll want to plug that in and verify that it does indeed work. Okay. But then what's happening over here with the second one, right? We have e to the x equals -2. Well, I can tell you already, right, that doesn't make any sense, right? This is indeed a false solution. But I want you to think about why. Let's take a look at our graph of e to the x really quick. Graph of e to the x looks like this, right? Where those are two, usual points we look at. When e to the x equals -2, that's looking for where our red graph crosses this purple graph. But those are never going to touch, right? Because e to the x has a horizontal asymptote right here, okay? So by all accounts, right, this is the false solution. This is impossible, right? If you were to take it a step further, right, try and take the natural log, we'd get x as the natural log of -2, right? But -2 is outside of our domain. The natural log of 2, or the natural log of -2, is wholly undefined, and both of those are false solutions. Let's take a look at one more of these exponential style ones, okay? Let's go 3x e to the x plus x squared e to the x equals 0, okay? So the first thing that I'm thinking when I'm looking at this is I'm thinking, okay, it looks like I can factor some things, right? And I'm actually going to factor kind of out to either side, okay? So I'm going to factor an x out to this side, and I'm going to factor an e to the x out to this side, okay? And there's nothing special about that. I just think it keeps things a little bit cleaner. So what's going to be left in here, right? This term is a 3 x e to the x. The x gets factored out and the e to the x gets factored out. So we're left with 3. Similarly with this guy, we lose one of these x's and the e to the x, so we're left with x. Okay. And we know that this guy equals 0. But here's something to notice, right? For all values of x, right, e to the x is greater than 0 for all x. So that means no matter the value of x, I can divide by it. So that means that I can divide the whole thing by e to the x. And the nice thing that over here, well, that's 0 divided by some number, and we still get 0. Okay? But I want to caution you here, right? Like this division by something with a variable in it almost always runs us into trouble. Because when we're just dividing by x, we could be dividing by 0. But we're dividing by e to the x here, which is never 0, right? That's why we're allowed to rewrite this as x times 3 plus x equals 0, okay? And because of our zero product property, we have that x equals 0 or x equals -3, okay? We do want to check our solutions, right? Because we did this, weird division here. That might have introduced some weird terms, okay? So let's check x equals 0. Well, we're going to have 3 times 0, e to the 0, plus 0 squared, e to the 0. Both of these zeros are going to annihilate everything in that term, and we do indeed get 0, okay? But what about -3? We're going to have 3 times -3 plus e to the -3 plus -3 squared e to the -3, okay? Well, that's going to equal, it looks like -9 e to the -3. It's like plus 9 e to the -3. Both of those are going to cancel, and we do indeed get 0. So all of these equations, right, these were all dealing with things that were primarily in the language of exponentials, okay? So the natural next question is, what about the logarithm? Well, one thing that's nice to notice, right, is because our logarithm is 1 to 1, so say log base a of x equals log base a of y. Because this logarithm is 1 to 1, that immediately gives us that x equals y, right? And I do invite you, go ahead and try a little derivation of this, sort of going through exponent land, because I think it will give you some good practice with, that sort of abstract algebraic manipulation. But either way, let's dive into solving some equations, okay? So let's say we're looking at log of x squared plus 1, and we'll set that equal to the log of x minus 2 plus the log of x plus 3, okay? Using our log laws, right, we can write this as log of x squared plus 2, or x squared plus 1. And because I'm adding two logs here, I can instead multiply their arguments. Expanding these out, I have log of x squared plus 1 equals the log, looks like x squared plus x minus 6. Okay. And using this property here, right, we can cancel these logarithms. We can get x squared plus 1 equals x squared plus x minus 6, right? The sort of reasoning behind what we're doing there is we're raising 10 to both of these powers and getting a bunch of nice stuff canceling, okay? When we go to rearrange this, our x squareds cancel, we move our -6 over, and we get that x equals 7, plain and simple. Okay, go ahead and, go back and check that to convince yourself. I guess I'll name this guy A, right? Just so that I don't need to write EX and then my little bar over and over again. Take a look at our next one of log base 2 of 25 minus x equals 3, okay? And this is why it was useful to note that the way we got rid of this was going 10 to the stuff, right? because there's no logarithm over here, none at all. But what I can do, right, since this stuff equals that stuff, I know that 2 to this stuff equals 2 to that stuff, okay? So that gives me 2 times the log base 2 of 25 minus x equals 2 cubed, okay? We have 2 to the log of stuff, right? That's why we chose a base of 2. So that means those are going to cancel. We're going to be left with 25 minus x. And 2 cubed is 8, right? And we follow this through, moving that 25 over, multiplying by -1, and we get that x is 17, okay? Continuing with these sort of similar problems, right? Let's go one that's a little bit more involved, but still kind of follows the same structure. Right, we'll go 4 plus 3 times the log 2x equals 16, okay? We move that 4 over, we get 3 times the log of 2x equals 12. We can divide by that 3. We get the log of 2x equals 4, right? We can go 10 to the both of these, right? Raise both of these sides to the power 10, okay? And then we're going to get 2x is 10 to the 4, okay? Which means that x is 10 to the 4 divided by 2, or indeed 5,000, okay? And this value for x is rather large, so I would encourage you, plug that value in for x into the equation and just confirm that it does indeed work. One last one for our logarithms. I think you sort of got the idea from these series of examples. Okay. Let's take a look at something like this. Okay. Maybe log of x plus 2 plus log of x minus 1 equals 1. Okay. I see an application of the log laws here. Okay. So I can combine those. X plus 2, x minus 1. I want to raise both of these to the 10th power, right? That's going to cancel this log. So we get x plus 2 times x minus 1 equals 10, right? I can expand out this multiplication to x squared plus x minus 2. Moving over that 10, we're going to get x squared plus x minus 12 equals 0. And this is going to factor nice and neat to x plus 4, x minus 3. That's going to give us two solutions of x equals -4 and +3. Go ahead and plug those in on your own, see if both of them work, see if only one of them works, and I'll see you in the next part.